Hello everyone and welcome back once again. In this video, we are going to talk about iron carbon phase diagram. So in the part 1 of this topic, we have seen several aspects of the iron carbon phase diagram. And in this video today, we are going to cover the part 2, which will describe the other aspects of this particular phase diagram. So we have started this topic on iron carbon phase diagram in the previous lecture, and so far we have gone through the basic details of this particular diagram, which is very important in the sense that the entire steel technology is based upon this particular diagram. Okay, so we have some understanding as to why is that so, and we have also seen the different phases that exist in this particular system. So just to have a quick recap, these are the phases that you will get in iron carbon system. Alpha or the ferrite phase, which is BCC in structure, and the range of temperature in which it exists is from room temperature to 910 degrees Celsius, as you could see from here also. And then we have the austenite phase, which exists from 910 degrees Celsius till 1394 degrees Celsius. And this phase is FCC in structure. Okay. And we have also discussed as to why the solubility of carbon is much higher in the FCC austenite phase compared to the VCC ferrite phase. Okay. So that has to do with the sites, or rather the size of the sites in which carbon atoms sit. Okay, the interstitial voids that you have. When you compare the size of those voids in the VCC and the FCC structure, you would find that the size of these voids is bigger in case of the FCC structure, and that is why it can accommodate more carbon, and as a result of that, the solubility of carbon in the austenite phase is higher. Okay, and then we have two more phases that you come across here. Delta ferrite, which is the high temperature BCC phase that exists beyond 1394 degrees Celsius. And then we have the cementite phase, which is again a very important phase here, because the presence of cementite will be almost invariable in most of the microstructures that you would come across in many steels, right? And we have also seen that this particular phase also forms the limiting boundary on the right hand side of the phase diagram. Okay, so 6.67% is the solubility of carbon in cementite, and that's what you see right on this boundary over here on the right hand side. That is where this particular diagram is terminating, right? So that vertical line at 6.67% basically represent the cementite phase. Okay. And then we have also discussed about different invariant reactions that you have with this particular system, and these are basically the peritectic reaction that you have at 1495 degrees Celsius over here. Okay, so here you could see around this region at this particular point, this is around about 1495. And the peritectic composition is 0.17% carbon. Okay, right? So it is this particular reaction over here at 1495 degrees Celsius and 0.17 carbon. Okay, liquid will react with the delta ferrite phase and form the austenite phase. And then if you come down here at this point, 1146 degrees Celsius and 4.3% carbon, then you have the eutectic reaction where the liquid is transforming into austenite and cementite. And then we have this solid state transformation here at around 0.8% carbon and 727 degrees Celsius, in which the austenite phase transforms into ferrite and cementite. Okay. So as I said, the microstructure of steel and the heat treatment of steel to generate different kinds of microstructures is mostly centered around this region here, and it also revolves around this particular transformation, that is the eutectoid. Okay. When we talk about the heat treatment of steels, you would see that this fact that this particular transformation becomes very important. Okay. So we have to talk a little more about it as to how this transformation occurs, what could be the mechanisms, and what do you see in the microstructure. Okay. So that is what we can discuss today. Now, when you say that this phase is forming, this alpha plus cementite phase is forming from the austenite. First of all, there is a name to it, this mixture of ferrite and cementite. Okay, that is known as pearlite. So, like how we have seen for the eutectic case, there is a mixture of two solid phases, right? So here also in the eutectoid reaction, which is the solid state equivalent of the eutectic reaction. So here also you would see a mixture of two solid phases forming from a single solid phase. Okay. So that particular mixture of ferrite and cementite, that eutectoid mixture of ferrite and cementite is known as pearlite. Okay, and this forms in a particular morphology also. Okay, so I would have shown you for the eutectic also that it forms in a particular morphology, taking what is known as a lamellar kind of structure. Okay, where you see this lamellae of these two phases, these two solid phases existing together in some colonies, right, across the material, across the microstructure. So a similar thing could be seen here also. These two phases that you have, ferrite and cementite in the pearlite, will form in that particular lamellar kind of morphology. Okay. So if you have a look at that, the schematic of that, this is how it looks like. Okay, I will show you a real micrograph also, which is taken on a steel which forms this kind of structures. So this is how it would look like. The black color lamellae that you see, that is the cementite phase. And the white areas that you see in between, that's the alpha ferrite. Okay, and you could see this is forming in alternative lamellae, right? Cementite ferrite, and so on. Okay, so as I said, we are going to discuss about that particular mechanism as to why this forms in a particular morphology like this in alternative layers or lamellae. Okay, so if you go through the mechanism, it will become clear as to why it forms in such a manner, giving rise to a morphology, a lamellar morphology like this. Okay, so we are going to come back to that and discuss a little more about the mechanism of this particular transformation from austenite to pearlite. Okay, what else we have before that? Let us see. Right, so like how we have in case of eutectic, hypo and hyper eutectic, here also we have hyper and hypo eutectoid steels. Okay, so anything which is left of the eutectoid point, right, that is your hypo eutectoid, and this region above 0.8% carbon, that is hyper eutectoid. Okay. So you could have, depending on the composition, two types of steels, hypo eutectoid and hyper eutectoid. Okay. You could also have a steel of eutectoid composition if the carbon content is around 0.8%. Okay. So, we have to then see what kind of microstructure you will have for the hypo-eutectoid steels, what kind of microstructure will develop for hyper-eutectoid, and then what microstructure you would get in case of a eutectoid steel. Okay. So, let us see that, and then as I said, I will also discuss about the mechanism of this particular transformation, the mechanism of the eutectoid transformation. But before that, let us also quickly have a look at the crucial temperatures that we have in this particular system. So, these critical temperatures, some of them we have already discussed, that is the eutectic temperature, the peritectic temperature, and also the eutectoid temperature. Now, there are some boundaries that you could see separating one phase from the two phase region, right. This boundary, for example, here this boundary. So, they also have certain significance in this particular system. And then apart from that, you also have, of course, the eutectoid temperature itself at 727 degree Celsius, and it is given a different name depending on whether you are cooling or heating, okay, and letting the eutectoid transformation to occur. So, if you are doing it during heating, then this will be marked as AC1, and for the cooling case it is marked as AR1. Okay. There is some meaning to it as to why it is written in that form, these three terms. These are basically French, okay, and the meaning of these are as follows, what you could see on the slide also. A stands for array or arrest, because you are heating or cooling, so at that particular temperature, you are encountering something. So, it is kind of an arrest over there, where a transformation is occurring. Okay. So, that is what A stands for, and then C is for heating, which is this term sous-phase, which means heating. Okay. So, that is a French word, the meaning of which is heating, and then R is given for the cooling. So, the cooling word in French is this refroidissement, that is the synonym of cooling in French. So, the R stands for that. Okay. So, depending on cooling or heating, this eutectoid line could be given these two nomenclatures or designations. Okay. And if you do heating or cooling, there could be a little difference in the eutectoid temperature. Okay. So, generally AC1 is greater than AR1. Okay. So, during heating, this temperature will be generally little higher. Now, these two lines are there separating the single phase from the two phase region. This one over here, this is alpha plus gamma, right, and on the right hand side this is gamma plus Fe3C. Okay. So, this two phase region is separated from the single phase austenite region by this line, that is A3, and this two phase region is separated from the austenite phase by this line, which is indicated as ACM. Okay. So, these are the two lines separating the single phase austenite from the two phase regions. Okay. There is one more in between A1 and A3. So, A2 was assigned to a kind of transformation that you see for the other temperatures also, for the other lines also. So, in the beginning it was thought that if these lines indicate a particular transformation, why not that line also between A1 and A3. So, there used to be an A2 line, okay, But then it was found that along that particular temperature in this system, there is no phase forming as such. There is nothing new, no new phase is coming. But still, some kind of change is occurring. So because of that change, it was first thought that some new phase is forming. But experimentally, nothing was found in the microstructure. Okay. Then, people thought that what could be the reason for that change. Some change was noticed. Okay. So if you heat iron or steel to a high temperature, what could you expect in terms of some properties apart from the mechanical properties? Can you think of any other property which will change as you heat it? Yes, magnetic property. The Curie temperature. So if you heat it beyond Curie temperature, the ferromagnetism that you have in iron will be lost and it will turn to paramagnetism. Okay. So that A2 temperature, that is between A1 and A3, is basically that Curie temperature, which is around 768 degrees Celsius for iron. Okay. So some change was noticed because of this magnetic to non-magnetic transformation. Okay. Some change in properties would have been noticed, but no new phase as such forms at that particular temperature. Okay. So these are the different critical temperatures that you see in this system. Okay. First of all, the Eutectoid temperature, the line corresponding to that. Then you have these two lines A3 and ACM separating the two phase regions from the single austenite phase. And of course, in between you have the A2 temperature, which is the Curie temperature for iron. Okay. Okay, now let us come back to this again, this hypo and hyper eutectoid compositions, okay, and see how the microstructure would develop when you cool a steel, let us say, from the single phase austenite region. Okay. So the steel is heated to a single phase region first, anywhere here, any temperature here above this, okay, and any composition which is left of the eutectoid. So it could be like this, for example, right, 0.3 or 0.4% of carbon, let us say. So as you cool it down from the austenite region, first of all it will encounter this boundary over here, the A3 boundary, right. So that is where you expect the alpha phase to form first, okay, from the austenite phase. So what is this alpha phase at this particular temperature over here? If we call that as T1, alpha is going to nucleate, right, but this is not the eutectoid alpha, isn't it, because eutectoid reaction has not yet started, right. So that means this is the pre of eutectoid. In our metallurgical term we call it pro, right. So it is the pro eutectoid alpha, isn't it. Right, and as you lower the temperature further, the fraction of this pro eutectoid alpha phase will increase, and that can be found by a tie line if you want, right. We have already learned it. Any temperature here you could find out what is the fraction of this alpha phase and the corresponding fraction for the austenite phase also, right. So as you lower the temperature, the fraction of this alpha phase will increase, and then as you come to this temperature, the eutectoid temperature over here, and just go little below that, the eutectoid reaction will occur and this eutectoid mixture, that is pearlite, will form, right. Okay. So right here in the single phase region, this is only austenite that you would see in the microstructure. Okay. here just below this point, just below T1, the pro-eutectoid alpha phase will start nucleating at the boundaries of this austenite phase. Okay. And as you lower the temperature, this alpha phase is going to increase in content. Okay, the fraction of the alpha phase will increase, right? And then as you come down to the eutectoid temperature, this remaining austenite phase that you have, that will transform into pearlite. Okay, so in the final microstructure, what do you expect? You have this pro-eutectoid alpha, which has already formed before the eutectoid reaction, and along with that you have the eutectoid mixture of alpha and cementite or the pearlite phase. Okay. So in the final microstructure of any hypo-eutectoid steel, you would find this alpha phase, the pro-eutectoid alpha and the pearlite. Okay. So let me see if I could show you a microstructure of that. Okay, the real microstructure. All right, so this is what you would see. So as I said, this pearlite would form in a particular lamellar kind of morphology, and it would form in pockets or what we call as colonies. Okay. So the gray or the black phase that you see, you could see, if you take a close look, basically you would see alternate lines or alternate layers or lamellae of these two phases, ferrite and cementite. So the black lamellae that you see in these areas, for example, this particular region over here, if you follow the cursor, here you could see this kind of lamellar structure, right? The black phase followed by a white region and then again a black lamellae and so on. Alternative layers of cementite and ferrite. Okay. So the black one is a cementite, and in between two black lamellae, the white portion that you have, that is the ferrite. That is the eutectoid ferrite. But apart from that, you have lot of these white grains, right? For example, here and here and here. Okay. So this is the pro-eutectoid alpha phase. Okay, which is formed before the eutectoid reaction, and whatever gamma phase was remaining, right, that has transformed into the pearlite that you see in these colonies around these black regions. Okay. So this is how the microstructure of a hypo-eutectoid steel look like. Okay. The pro-eutectoid alpha phase, that is the white grains that you see over here, and the pearlite, the black grains. Okay. All right. So now if we have understood this, the microstructure development for the hypo-eutectoid composition, it is also easier for us to now understand what would happen for the hyper-eutectoid composition. Okay. In a similar manner, the microstructure is going to develop as you lower the temperature from the single phase austenite region. Okay. But the only difference would be, instead of formation of the pro-eutectoid alpha phase, in the hyper-eutectoid case, the pro-eutectoid phase will be cementite. Okay. So the cementite phase is first going to nucleate from the gamma phase, and then as you lower the temperature, the fraction of this cementite phase would increase, and as you come down to the eutectoid temperature, the remaining gamma phase will transform into pearlite. Okay, and in the final microstructure, therefore, you would see this pro-eutectoid cementite along with the pearlite. Okay, in a similar manner how you see for the hypo-eutectoid case. Okay, and for the eutectoid composition, what will you see? What will you observe in the final microstructure, and how the microstructure would develop? Yeah, it is all, it will be a complete lamellar structure in the final microstructure, because here there is no pro-eutectoid phase, only the gamma phase is going to transform into two phases or a mixture of two phases, ferrite and cementite, which is known as pearlite. Okay. So, if you look at the eutectoid microstructure, then it would appear like this, completely pearlitic. So, let me see if I have a fully pearlitic microstructure, maybe not. Yeah, but anyway, these white regions that you see, those will not be there. It will only be these black grains containing these lamellae will appear all over the microstructure. Okay. So, it will be 100% pearlite. Okay. So, from now on, we could do one thing when we discuss about the steels, as to how different grades of steels are made by heat treatment to develop a particular type of microstructure. We could ignore the right hand side beyond 2%. Okay. So, if we do like this, that should be enough for us to work with. Okay, so this will be the steel portion of the iron carbon phase diagram. And as long as we are dealing with steels, I think this part alone should be enough. Okay. So, whenever we discuss about steels, like how the microstructures of different steels are developed by heat treatment, we will come back to this part only. Okay. And as I would have mentioned before, it is all about this particular transformation now, the eutectoid transformation, which you need to consider when you talk about heat treatment of steels for developing different types of microstructure to generate different grades of steels. Okay. So, here other thing that by now you would have noticed that this phase is actually always coming, and it is also forming the boundary of the entire iron carbon diagram that we have seen so far, right. So, it is like a component being present in the system, right. It is like the B component of the phase diagram. If you have a phase diagram between A and B, we know that the phase diagram terminates at B, right. When you see the composition in terms of percent B, then at the right hand side it terminates at 100% B, right. So, here also you have seen, right, if you go back to this, it is terminating at the cementite line. So, cementite is like a component here rather than a phase. That is why many a times this is also referred to as instead of iron carbon diagram, it is referred as iron carbide diagram, because of that fact that cementite is present like a component. Okay. So, this diagram that we have considered so far, it is basically this iron carbide diagram. If you want to consider it in terms of carbon, then probably you have to go back to the portion of the diagram where carbon can exist as a component or as a phase. Okay. And what is that phase of carbon or that state of carbon which will come in here? If carbon has to be present as a free carbon, then in what form it can be present? Graphite. Okay. So the iron carbon diagram then basically belongs to the graphite phase and not really the cementite phase. Okay. In other words, you could say that cementite is not a very stable phase. We could say that it is something between stable and not stable, a condition known as metastable, something in between. Given enough time and chance, this phase would tend to dissociate into its components, that is iron and carbon. So free carbon would come out from it and iron will go back to the parent material. But in the steel, the conditions and the compositions that we have in steels, this process of dissociation will take huge time. It will happen, but maybe several years of time it will take. That is why in steel you would not find a free carbon in terms of the graphite, right? But when the carbon content is increased beyond 2%, then there are favorable conditions for this dissociation to occur, because now carbon concentration itself is high. So it has more chances to come out from this Fe3 phase, this Fe3C phase and be present as free carbon, as graphite. Okay. So that could happen beyond 2.1% of carbon in materials having more than 2% of carbon. Okay. So that material is cast iron. So when you talk about cast iron and you come back to the phase diagram to correlate anything with regard to cast iron, you have to talk about the iron graphite phase diagram or iron carbon phase diagram. And you would find little bit of difference in terms of these boundaries, in terms of the temperature at which these boundaries would form. Okay. So this is another thing that you should remember when you talk about the iron carbon phase diagram. Okay. So there are two aspects of it. One, you are looking at it with regard to the cementite phase, when you are considering that cementite is very stable and it is not going to dissociate as such. It may dissociate, but over a very long period of time. That is the steel part of it. But when you say that we have more carbon into it, more than 2%, then basically we are saying that carbon in free form can also form and be present as a phase, as graphite. So then you have to consider a diagram which depicts that condition in terms of the presence of a free form of carbon, right? So then you have to draw this diagram little bit differently, probably some dashed lines here and there, it will come like this for the eutectoid, let's say, little different or little up and down compared to the iron Fe3C diagram. Little bit of differences you would see. Rest of the things and how the phases coexist, the equilibrium, all those things will remain the same. Only difference being, as I said, because of the presence of free carbon, you might see some differences in the phase boundaries in terms of the temperature. Okay. So just remember that.